Hello students, welcome to EPG Pathshala. I am Dr. Nasir Iqbal from Department of Physics, University of Kashmir, Srinagar. Today we are going to talk on the module the Photometry-II under the paper of Astronomy and Astrophysics. After completing this module, the students will be able to learn the following things. Number one, different types of detectors which are used in the astronomy for photometry. Basic idea about how photographic emulsion and photomultiplier tubes are used as detectors in astronomy. A detailed description about the development of CCDs as detectors, the construction and the mode of operation of CCDs as detectors. So let's start from the basic definition. About the astronomy, we know that astronomy is an exciting field to study. The marvelous pictures of many celestial objects taken by using large ground and space-based telescopes are the most visible manifestation of modern research astronomy. Pictures are needed as a first step in classifying objects based on their appearance, that means the morphology. However, the transition from observational astronomy to science requires the quantitative information about the celestial objects. The quantitative information is the measurement of the properties of the object, such as how far an object is, how much energy does it emit, and how much hot it is, which is related with the temperature of that very object. The amount of energy in the form of electromagnetic radiation that we receive from celestial object can be referred as a flux. The science of measuring the flux we receive from celestial objects over broad wave lengths bands of the radiation is actually called the photometry. Measurement of flux, when combined with some estimates of the distance to an object, can give us information on the total energy output of the object, that's its luminosity, the object's temperature and the object's size and other physical properties. Photometry is the measurement of electromagnetic radiation received from the various celestial objects. This response changes with wavelength and to the extent from person to person. In photometry, the word luminous is used to indicate that measurements have been made using a detection system called as a photometer that has a spectral response similar to that of a human eye. Telescopes simply collect photons. To make useful observations, it requires some sort of to detect those photons and make a measurement or record of them. The natural detector of visible photons is the retina of the human eye. However, eye is not a very good photometric device in the sense of being able to make quantitative measurements of flux. Also, the eye is not an integrating device, that is, signal doesn't build up with time. The eye does not provide a permanent record of what it sees. Thus, eye is not used as the primary detecting device at professional research level telescopes. Thus, there was a need for a technological advance in astronomical detectors. The functional components of a detector are position sensing component, total energy measurement component, timing component, particle identification component. When we talk about the detectors, detectors in astronomy are basically of three types. The main are the photographic emulsions, the photomultiplier tubes, and the charged coupled device to be abbreviated as CCDs. Let's talk about the photographic emulsion. The importance that the photography could have in the field of astronomy was realized by Louis Jacques. It would allow an accurate, easy recording of brightness, position, spectra, and physical aspects of celestial bodies. However, the early photographic palettes weren't so sensitive enough to image faint objects. During the decade of 1870s, there were several dramatic technological breakthroughs in the field of photography. In 1871, Richard Leach produced the first positive dry emulsion for physical development using gelatin, and then in 1874, Johnson made the first negative emulsion for chemical development. Later, Charles Bennett increased the speed of the sensitivity of light of gelatin silver bromide emulsion by aging them at 32 degrees centigrade in a neutral medium. This was the first technological advance in astronomical detectors. Since the universe is filled with very faint objects and astronomers wanted to be able to photograph them without waiting for days to get an image on photographic plate. Emulsions help up in the study of the spectra. The first good photographs of Jupiter and Saturn were made in long back 1879 and 1886, and of comets in 1881 by using the emulsions. However, emulsions are not very good photometric devices for astronomy because of several drawbacks. Photographic emulsions can make a permanent record of astronomical objects imaged by telescopes. However, photographic emulsions are not supposed to be good photometric devices because of several drawbacks. These record a small fraction of around 1% of the photons that hit the emulsion, and because of the analog rather than the digital nature of the image record on an emulsion, it is difficult to make the quantitative measurements of the star's brightness. Photographic emulsions are also non-linear. Twice the input light does not produce twice the output on the film. This features is called the reciprocity failure. Photomultiplier tube. Photoelectric photometry is the electrical measurements of the light intensity of stars and other objects. Photomultiplier tube, which generally we write as PMT, is one of such detector which finds extensive use in photometric observations of stars and other objects. The functioning of the photomultiplier tube is based on the well-known principle, that is the photometric effect, which converts light energy into the electrical energy. A photomultiplier tube consists of a light-sensitive photocathode which emits photoelectrons at a rate modulated by the signal, and a multiplier section which amplifies the signal to provide a measurable current output. Photomultiplier tubes are sensitive to radiant energy from the ultraviolet about 105 nanometers to the near infrared about 1100 nanometers. Their ability to detect signal photons makes them particularly useful in low light astronomical applications. The PMT is the first modern detector. It is inherently digital. It detects individual photons and outputs a number which is directly and linearly related to the number of photons that were incident on the detector. A PMT consists of an evacuated glass tube, one end of which is deposited a film of material such as indium antimonide called as photocathode. This material has the property that when it is struck by a photon, an electron is often liberated from the material. Each electron liberated from the cathode is directed away from the cathode by an electric field and is amplified into a pulse of electrons by a series of metal pellets called as diodes and an accelerating electric field in the tube. Electronics coupled to PMT count these pulses. Thus, a single photon hitting the cathode results in an easily counted pulse of many electrons. In the search to understand the universe, the astronomer seeks even more powerful observing instruments. Today, progress in optics, thin mirrors, materials, light and rigid structures, and computer sciences, image quality improvement in real time allows giant telescopes to flourish around the world. Compared to the ancestors of just 20 years ago, new telescopes are often located without regard to on-site living amenities. Rather, the controlling factors are the maximum number of clear nights and calm transparent atmosphere. The atmosphere is often found half a world away sitting comfortably in front of a computer screen from which he controls the telescopes and collects the data via satellite link. Throughout the history of the telescope, the sensor at the focal point has been recognized as vital. Nobody can afford to waste the few rare and precious photons gathered by expensive telescopes because of an inadequate sensor. The practical sensor has been the human eye. However, its sensitivity, limited by psychological considerations and human subjectivity, placed serious limits on what could be discovered. The advent of photography in the last century was a monumental step forward. A fundamental advantage of photographic palette is its ability to record unseeable faint stars with long exposure times. Photography technology has evolved over the years with ever more sensitive emulsions and treatment techniques. Despite these improvements, the efficiency of a photographic palette remains relatively low. For every 100 photons that strike the palette, the best only 3 or 4 react with the silver sensors in the film emulsions to create the image are selected. This means that 1 meter telescope using photographic techniques is no better than a 20 centimeter telescope equipped with a 100% efficient sensor. We can therefore understand why the astronomers continue to seek a better sensor like 3 to 4% efficient photographic palette. Modern detectors are inherently digital. The first modern detector in this sense is the photomultiplier tube. Photomultiplier tubes offer various interesting advantages. Extremely fast response time. Reaction time can be as short as a fraction of nanosecond. PMT allows the measurements of very weak signals with signal to noise ratio limited by electron statistics. The nature of output of a PMT enables application of pulse counting technique. The drawback of a photomultiplier tube is that it is essentially a single channel device, meaning there is no positional information in the signal. The output signal does not depend on whether on the cathode the photon will hit or not, so we get only a measure of all the light following on the photocathode. However, the PMT, unlike a photographic palette, has a digital output, meaning we can easily make qualitative measurements. The fraction of the photon which hit the cathode that are actually detected by the photomultiplier tube is set by the fraction of the photons that hit the cathode that liberate an electron. The fraction is typically 20% or so, so the efficiency of observing is much higher for a photomultiplier tube than for the best photographic emission. The detector of choice for optical astronomy is now the CCD charge coupled device due to various advantages. Let's talk here about now the charge coupled device. Generally, we call it as the CCD. A charge coupled device is a device for the movement of electric charge, usually from within the device to an area where the charge can be manipulated. For example, converting it into a digital data. Most astronomical detectors in use today at professional observations as well as with many amateur telescopes or charge coupled device. The charge coupled device image detector was developed way back in 1970 by Boyle and Smith at Bell Laboratories. The original CCD was designed to store and transfer the analog information in the form of packets of electrical charges within a semiconductor structure. The charges have memorized in strong sites, usually composed of MOS capacitors, that is metal oxide semiconductor type of capacitors. There can be several hundred to several thousand MOS capacitors on a single silicon chip. The sites are coupled together by transfer circuitry, which makes it possible to move the charges in an orderly manner to a point where they can be measured. CCDs have various uses: memories, delay lines, correlators, and optical detectors. The last category is of most interest here. That means the optical detectors. In photosensitive detector with CCD registers, the electric charges are created through the photoelectric effect. The storage sites are also photoelements. They are sensitive to light. They are organized either in lines or in matrix. After a period of being exposed to light called the integration time, the photocharges are transferred one behind the other to an output stage. The electrical signal delivered at the output voltage or the output stage is proportional to the incident illumination falling on the red photo side. We therefore observe at the output the variation of an electric signal synchronized with a read out rhythm of the CCD and correspond to the number of charges contained in the packet. The injection of charges, their storage, their transfer, and their readout are the basic functions of CCD. Now, what is the main principle of operation here? Basically, a CCD is a light sensitive silicon chip which is electrically divided into a large number of independent pieces called pixels. Present day CCDs have 512 to 512 to at least 4096 into 4096 individual pixels for astronomical use. We use the CCD as a device to measure how much light falls on each pixel. When a photon is absorbed in silicon, an electron hole pair is created. in a CCD electrodes create potential wells in the silicon that collects these electrons. The surface of CCD is covered with electrode biased so that the electrons preferentially are diffused towards the electrodes with the highest applied potential. The holes diffuse away into the bulk of the silicon and are effectively lost. The output is a digital image consisting of a matrix of numbers, one per pixel, each number being related to the amount of light that was on that pixel. The image coming out in a digital form is readily manipulated, measured, and analyzed by computer. The mass capacitor. A mass capacitor is composed of a doped semiconducting substrate covered by an insulating layer of silicon dioxide on which a metallic electrode called a gate is placed. The insulating oxide is a thin layer of silicon several tens of micrometers thick. The metallic electrode is deposit of aluminum or polycrystalline silicon heavily doped to become a conductor. The layer of silicon oxide makes the mass structure insulating and forms a capacitor. So when we study the mechanism that stores the electric charge in mass capacitor, a silicon atom has its valence band occupied by 4 electrons. Each valence electron associates 2 by 2 with those of neighboring atoms to form a crystalline lattice. In the case of crystalline, 8 electrons would complete the valence band. If trivalent impurities are introduced into the lattice, each atom of impurity introduces only 3 electrons and there will be only 7 electrons in the outer layer. A hole is therefore created. The hole is caused by the absence of an electron, and because of the deficiency, we say that the semiconductor is a p-type doped. On the other hand, n-type semiconductors are doped with pentavalent atoms which have 5 electrons in the valence band. Suppose that the substrate is of a p-type doped silicon, as is most frequently the case with CCDs. The holes are then called majority carriers. There are several free electrons resulting from the action of thermal energy which breaks the covalent bonds and brings the electrons back from the valence band towards a band where they can move freely, the conduction band. These electrons are called mainly minority carriers. The gate of a MOS capacitor is biased positively with about 10 volts. At the instant that the bias is applied, the majority carriers, the holes present in the neighborhood of the silicon dioxide interface, are pushed back into the interior of the substrate. A zone that is almost empty of majority carriers is then created in the area of the interface. A zone where charges are rare is called a depletion zone or a space charge zone. A space charge zone is not in a state of equilibrium over time. Hole pairs are either generated from within the depletion zone or diffused at the frontier of this zone. These electron hole pairs are separated by the electric field and the electron accumulate in the neighborhood of the silicon dioxide interface. The concentration of minority carriers of a type opposite to those of the substrate creates an inversion layer. The presence of minority carriers reduces the voltage of the surface from V1 to V2. That means decrease in the thickness of the depletion zone, which can be seen from the given figure referred as CCD voltage well. After a certain period of time, called thermal relaxation time, there are as many electrons on the surface as there are holes in the substrate. The phenomena is known as the dark current. The state of current that results from the situation is reached between 1 and several dozen seconds after biasing the electrode. Relaxation time depends on the time of silicon dioxide on the state of the surface between silicon and the oxide and on the temperature. The CCD is used when the mass capacitor is in disequilibrium, that is, when the minority carriers produced by thermal effects are negligible. The useful electron carriers are those that are generated by photoelectric effect and not those caused by dark current. Useful electrons can only be accumulated for a period that is less than the realization time. These carriers are stored at the silicon dioxide surface, and the inversion layer thus produced carries the information. The operation of a charge injection, transfer, and readout must take place in a very short time compared to the thermal relaxation time. Now, here we discuss some basic concepts to these CCDs. For that, we talk about the quantum efficiency. A CCD detects individual photons, but even the best CCD does not detect every single photon that falls on it. The fraction of photons falling on a CCD that are actually detected by the CCD is called the quantum efficiency, usually expressed as a percentage. Another way of defining quantum efficiency is that involves the signal to noise ratio of the input and the detected signal. For CCDs, in which photon noise is the dominant noise source, the fraction of photons detected and the signal to noise definitions of QEs means quantum efficiencies are equivalent. Quantum efficiency is actually a function of wavelength. For optical definition, there are two basic styles of thick chips or front side illuminated chips in which the light passes through some of the electronic layers of the CCD before hitting the silicon detecting level, and thin chips or backside illuminated in which the silicon layer is mechanically or chemically thinned and the light enters the silicon directly. Thick chips have low quantum efficiency in the blue because the electronic layers absorb much of the blue light. Thin chips have better blue quantum efficiency. Thin chips and thick chips have more similar red quantum efficiency, but the thin chips usually have higher quantum efficiency at all wavelengths than the thick chips. Now we talk about the other part of this, that is, what do we mean by the dark current that is used in the phenomena of CCDs. The main enemy of the CCD user is the dark current. Even when the device is placed in complete darkness, a signal is observable at the output of the detector. This signal is the result of the charges created in the silicon because of the thermal agitation of the crystalline lattice. Charges of thermal origin are created in the photoelements as well as in the thermal resistors. We share the same technology as the CCD. Their number, like that of a photocharge, is obviously tied to the integration time. The production rate is such that at room temperature, a standard CCD in darkness is saturated after only a few seconds of integration. On the other hand, the dark current becomes nearly negligible at a temperature of about 100 degrees Celsius. Now, how to do the photometry with these CCDs? The mainstay of astronomy in photometry is to see that how it is related with the functioning of the CCDs. Technically, this means measuring the light output of an object such as a star or of a galaxy. In the past, photographic and electric photometers were used. The former is essentially obsolete and the latter is not so accurate. The great advantage of CCD detectors is in their quantum efficiency, which enables us to use not only big telescopes in major observatories but also small amateur ones for unique data collecting. This opens up many new opportunities in the astronomical research. Example: long term monitoring of variable stars, search for new variable stars, search for supernova, eruptions in other galaxies, search for near Earth astronomic asteroids and their photometry. The image produced by a CCD camera is by a number of astronomical effects which must be correlated before reasonable results can be obtained. The image which is not yet corrected will be called a raw image. The raw image contains not only the information about the objects of interest but also a contribution from the electrons introduced by read noise and thermally generated electrons. The process of CCD image reduction. The process of CCD image reduction is based on the use of three calibration images: the bias or offset frame, the dark frame, or flat field frame. So, few things which are also important to know what we mean by the bias frame. Despite the fact that CCDs are inherently linear, there is an offset or signal even with no exposure. This is called the bias level. A bias frame, that is an image of zero duration with the shutter of the CCD camera closed, can be taken, stored, and then subtracted from every exposed frame. The preferred practice is to use the average of several bias frames. Dark frame. The frame is exposed with a closed shutter, usually with the same exposure time as the raw image. The dark frame measures the thermal on the CCD chip during exposure. The dark frame can also give information about bad or hot pixels on CCD chips as well as an estimate of the cosmic ray strikes at the observing sites. Flat field. The frame is used for correction of the pixel to pixel response variations. These pixel to pixel sensitivity variations also change with the wavelength of the incident light. Flat field frames could be obtained by illumination of the CCD by constant and uniform light to provide the high S by N image. The benefits of the photometry with CCD are many. Few of them are: all objects are observed by the same detector and through the same filter. The high quantum efficiency, which depends on the spectral range, may reach up to 80%. The great advantage of CCD photometry is that more than one or two comparison stars can be used at a time. Sky background can be estimated directly near the major stars, and contribution from other sources could be eliminated. Photometers are unable to do crowded field photometers as unwanted star may drift in and out of the aperture. Also, the comparison stars must be chosen ahead of time and cannot be easily changed during the night. With CCDs, this is not the problem as the entire field view is saved. This allows data reduction using varying aperture flat that can be compared to ensure that only the flux from the target star is observed, and also the companion star can be chosen at the time of reduction with as few as many as the observer. So students, let us see what we are going to learn in this very module. We have discussed the photometry, the concept of the photometry, the phenomena of the photometry, its importance, and then we talked about the detectors. Then we can learn more about the photographic emulsions, the photomultiplier tubes, the charged coupled device, and certain concepts of the CCDs, and how the photometry is being carried with CCDs, and then summarize all these discussions. Thank you.